Hello friends, I'm Ram Lakshmanan, architect of White Crash. Friends, I have come here to Montreal, Canada to speak in the Confu conference on the topic memory patterns to predict production outages. I thought I'll give a quick recap of this conference talk with all our viewers, right? Okay, so let's get started. Friends, memory is a finite resource, right? So let's see what's happening. Let's say here is my application memory. Let's say when a new request comes, to service this request, we end up creating a lot of objects. Let's say a sign-on request comes. We create a customer object which will have a username and the password, and then I create a DAO object, I create a controller object, I make a connection object to make a call with the backend database. The backend is going to give me back a record set, which is an object, which will have fields, which are once again objects. So we create like a lot of objects to service even a simple sign-on request. Okay, I created these objects and then I serviced my request. Now my request goes away. After the request goes away, what will happen to these objects? Right? These objects needs to be evicted from the memory. They have to be removed from the memory. So the space is created, so the room is created to service new incoming request. Right? So this is called as evicting the unreferenced objects from memory is called as a garbage collection, right? So we want to study our memory patterns with the garbage collection behavior, right? So now let's look at it. So this is an garbage collection behavior or a memory pattern of a very healthy application, right? Don't worry how to generate this kind of a graphs. I will talk to you about it towards the end of this session, end of this talk, okay? Look at this, friends. Look at this memory pattern of a very healthy application. This is a very healthy application. Here you can see the request comes, the memory builds up. This red triangle indicates it's a full garbage collection event. So now a full garbage collection event ran and the memory is dropping all the way to the bottom. And now request comes, the memory is building up. Now a full garbage collection event runs and the memory is dropping all the way to the bottom. I can see this beautiful sawtooth pattern. But one thing, friends, look at this in the bottom, right? Here there is this line, a slope. If I put a slope, here it's going at 0 degrees. Right? It's going at 0 degrees. Look at all the bottom points. It's going at 0 degrees. So this is one pattern of a very healthy application. Now let's look at another pattern. This is a pattern number 2. Look at this, friends. This is what is the difference you see in between this pattern and then the earlier one. Here also I see this sawtooth pattern, like I see going up and down, going up and down. Do you see any difference in between the previous pattern and this one? The difference is, you can see in the earlier graph, these bottom points were touching almost coming all the way to the bottom. Right? In this case, it is not coming. Right? It is here, right here, it is at a 40 GB itself. It's not coming all the way to the bottom like in the earlier graph. So this, what does this tells you? This tells that this application is caching a lot of objects. There is a heavy caching is happening. That's why this is not able to come down. And friends, if you take this graph and show to your developer team, that will be revealing to them. Oh, are we caching this much? It may be kind of revealing. So you may want to see whether your application is following this pattern. And if you are caching this much, sometimes most of the time, people doesn't know why they are caching this much. And maybe they can remove several of them and can conserve your memory. Right? Now, let's move on. Pattern number 3. How does this graph looks to you? Any observations on this? Right? Here I can see the request coming, the memory building up. Now a full garbage collection event runs. It removes unreferenced object. Now memory is dropping here. Now still once again memory builds up. A full garbage collection event runs. It's dropping. Any observations on this pattern when compared to the healthy pattern, the pattern number 1 that we saw earlier? Friends, look at this. If I put a slope, right? Here I put the slope. Put a slope is a high school mathematical formula, y is equal to mx plus b. But people today, they're calling this as machine learning. Right? Okay, that's good. So here is this slope. Look at the slope. This slope is going at a 15 degrees. It is not going at a 0 degrees like the earlier one. So when it goes at this kind of 15 degrees, it is kind of telling this application is having an acute memory leak. Right? It's not very aggressive enough, but it is having acute memory leak. If this application continues to run, it will experience memory problems, right? It is already getting evident here. So right here itself, I can predict and forecast and say, oh, this application is going to have an outage in several hours, right? I can say that. Now look at this pattern number 4, which is very interesting, right? You see, this is kind of, if that application would have run, is coming down, and after this point, it is not able to come down. This means this application is definitely having a memory leak. It is definitely having a memory leak, right? See friends, whenever even just one red triangle, it means a full garbage collection event is running. When a garbage collection event runs, it consumes enormous amount of memory. It consumes enormous amount of CPU cycles. Because friends, today modern applications, even for simple requests, we are creating tons of object. And now a garbage collector has to be running in concurrently with your application. Whenever it's creating object, it has to run in the background and check, oh, is this object being referenced? If so, who is referencing it? And then can I remove it? It has to do a lot of computation. To do such heavy computation, it consumes enormous amount of CPU cycles. So even when one red dot is there, at that point you're going to see CPU spiking up. But look at this, here the red triangles are consecutively running. It's running again and again and again. That means this application's CPU would be at a 99-100%. Right? After this point, it's going to be at 99 or 100%. Right? Several times you may have deployed to production, application would have been running all throughout the fine, but all of a sudden the CPU starts to spike up to 99-100%, and you didn't make any flag setting changes, you didn't make any code changes, but all of a sudden it starts to spike up. It could be one of the quite likely possibility is the garbage collection is running repeatedly again and again and again, right? And also friends, all our monitoring tools today catch up and they raise an alert, they start spinning that siren, the sounds, only at this point. But right here itself I can predict, oh, you're going to have an outage. So if I know here, I can take out my JVM from the production. Because after this point, look at this, it is running for several minutes or several hours until your site reliability team is going to come and decommission this instance from your load balancer. Until then, it's going to keep on running. Until then, as long as it runs, any request that is coming in, customers are not going to get any response. It's going to have a very negative customer impact. Rather, we want to avoid it, right? So, this is one pattern which was very powerful. Like you can see, when I see this, it's confirmed you're having a memory leak. Then you want to take a heap dump, and then you want to analyze that, what is triggering the memory leak. How to diagnose memory leaks, there is a separate talk in our channel which you can look at it, right? Okay, let's move on with the pattern number 5. This pattern, look at this. What is your observation? You can see here there is this full garbage collection events are running, application is struggling here. But after a point it dropped. Unlike the earlier example in earlier pattern, it was just keep on continuing. Here it is able to drop and it's able to recover, and application is able to perform well. What does this indicate? What does this indicate to you? This indicates right during this time frame, right, where my mouse is moving, maybe your application got a huge spike in traffic. Maybe this was your morning time, 8 a.m. to 10 a.m., right, where most of your customers are signing in. So at that point, there is an increase in the traffic, or there was a batch job was running, which was throttling in a lot of load to your application. Now it started to spike up, right? When this kind of a pattern happens, what it indicates, and it's able to recover after time, it indicates that your application needs more memory than what you have allocated. That's what it's indicating, right? Because of the spike in traffic, it's not able to handle during this period. So maybe during those period, whether do you want to look at allocating more instances to your load balancer so that the load can be distributed, and then you can scale back after that batch is completed or the peak volume traffic has gone. Or you can look at increasing your memory size, right? These are some of the alternatives you can do. This is another interesting pattern, right? Pattern number 6, look at this. Here it is going up, going down, but here I can see this repeated garbage collection running repeatedly again and again and again, right? Why this is happening? See, I can understand if this garbage collection is repeatedly running when the memory is at the peak usage. No, it is not at a peak usage. It is only here. And why when it's here it is running into this issue? Why the garbage collection had run repeated? Why shouldn't it has run when it has maxed out? Right? Friends, when you see this kind of a pattern, it means it is indicating the metaspace in your application, especially if you're running on a Java-based applications, the JVM. JVM has multiple regions, right? It has this young generation and the old generation, which together we call as a Java heap, and there's a metaspace where the metadata information about your application is stored, and then there's native heap. This is where the threads are running, the garbage collection, the connections are all stored in this native heap. And the metaspace is the region where you store the metadata information that is required, the class definitions required to execute your application is stored. What was happening in this pattern was the metaspace, that is one region, the small region in memory, was getting saturated. It was getting filled up. So that's why it was happening. So now when this happens, now you want to investigate just around metaspace. Why it is saturating and how to go about debugging it. See, below this, in each and every thing, I've given this report, right? You can click here and to learn more about it. Okay. Friends, so these are 6 different patterns. How do I go about generating these kind of garbage collection graphs which has this heap memory patterns? How can I get this data? Right, friends, to do this, you want to enable the garbage collection log in your application. You can enable the garbage collection log by passing these arguments to your launch-up scripts. If it's a Java-based application or Scala or Kotlin or any application that runs on Java virtual machine, you pass these arguments and give the location of your file path where the GC log has to be reported. When you give these arguments, the JVM will start to write the garbage collection statistics, the information into this GC log, the file path what you give. Java 8 or before, this is what the argument you want to pass. If it's going to be Java 9 and above, this is the argument you want to be passing. Right? This is what you want to be passing. When you do this, the garbage collection log file is going to be created. And friend, this garbage collection log file is a very large file, and it has a lot of nuances. It's not very easy to understand and look at it. So, even before that, one thing I want to share. And friends, always consider enabling the garbage collection log in all your JVMs, right? Because here is a case study we published. Enabling the GC log does not add any noticeable overhead, any observable overhead is not there. And it's very, very powerful to detect and predict these kind of patterns. And it's also helpful for several other things, like it can help you to reduce your cloud computing cost. It will help you to make effective capacity planning. It will help you to reduce your overall application's response time. All those benefits are there, which we have discussed in another video, which we will share in the description, right? So consider enabling your GC log on all production instances, which will not add any overhead. If your management is concerned or any fellow developer is concerned, here is a link which we'll share in the description as well. You can take a look at it, right? Where it's a detailed white paper showing it does not add any noticeable overhead. Okay, now we have generated a GC log file. This GC log file is a little bit a cryptic file, right? It's not readable. So here are, friends, some of the free tools which is available to analyze the garbage collection logs, right? These are some of the tools. Now, for our purposes, let me show you the GCEC tool, and then let's look at it. So here is this GCEC tool, right? Here is a GCEC tool. To this tool, I can come in, and then I can upload a GC log file. Right? Otherwise, it's very cryptic and very tedious file to read. Once I upload, this file contains a lot of rich information like key performance indicators, and here is the garbage collection pattern, the memory pattern what we're discussing, and what is the pause times which is there. It has so much metrics, right? Which you can use. Okay, friends. So these are 6 interesting memory patterns which can help you to predict your production outages. Okay. I will come back to you with yet another interesting session. Thanks for taking time to watch this. Thank you, friends.